Okay, any questions about the stuff we talked about last time before I continue? Last time, I'll refresh your memory about this. Last time we looked at the stiffness of the bolt. And to refresh your memory, well, I guess that picture is no good. Bolt is made of two parts, a threaded part and an unthreaded part. Of the threaded part, a fraction will be in the grip. So we did some calculations. There's the nut. We did some calculations and we found what this length was. We called it little lt. We call that ld. Then we said for each axially loaded member like this, we can define a stiffness as AE over L, where A is the cross-sectional area, L is the length, and E is the modulus of elasticity. We applied that equation to both parts. We got a stiffness for the threaded part, a stiffness for the unthreaded part, called KD and KT, KT and KD, respectively. And then we said these are two springs in series, so 1 over K, and I will call it K of bolts, the stiffness of the bolt, is equal to 1 over KT plus 1 over KD. And this will be equal to, if you take common denominator and write it out, AT, AD, E divided by AT, LD plus AD, LT. So that's where we were last time. In order to be able to analyze the stresses in the bolt and or the member once we tighten the bolt, we need to take into consideration not only the stiffness of the bolt, but also that of the member. And the stiffness of the member is a little bit more complicated than that of the bolt. The reason is that in the member, the area that's under compression does not remain a constant. In the bolt, the area that's in tension, yes, changes from the threaded part to the unthreaded part, but it remains constant throughout that length with AD and constant throughout that length with AT. That area for the member is not a constant. So we can't use that equation as is. We can use it in differential form to find a differential deflection or change of length, and then find the stiffness from that. So that's what we will be doing. And let me draw a arbitrary joint here with two members. I guess it could continue on either side. It doesn't have to end here. So there is a bolted connection right there. When we tighten the bolt and produce a preload, they are high loads here and here. Coming from the bolt head and from the nut as you tighten the bolt. Everybody okay with that, right? Now, this load from the underside of the bolt needs to be transferred to the top of the nut or vice versa. In other words, this grip that you have creates a force throughout this member. That's how we affect the joint. That's how the members are kept together. So the question here is, does this load travel through these two members straight down like that? In other words, if I take a look at this point here, I see no compression. Is that right? If I get away from the bolt head somewhat, and take a look at the member here, will I find that member under compression or not? Except in very, very rare cases, I hope so. Otherwise, you don't have a joint. What do we want to do? We want two pieces to be connected together. My two hands are the two parts of the member. So we put a bolt through that. We tighten the bolt. If this part up in my finger is not to have any compression, then this is what I have. I just have compression here on the bolt, and that doesn't make any sense. The parts are connected to one another. So this load travels somewhat. Now, how much, that is really not quite well understood. But we have some approximations that we can make, and we can use those approximations to come up with a good design for a joint. So running some experiments and just simply putting strain gauges here, all over here, we find that this load is transferred from the underside of the bolt head to the top of the nut in a trapezoidal form, two-dimensionally, like that. Actually, let me put that in a different color. Not a part of the joint, but the way the load travels through. Exactly the same thing happens down in here. So we get that. Now, if you take a look at this, and assuming that these two members are not of the same material, if they are, things are a little bit simpler, but assuming that they're not, taking a general case, then we see that we have one trapezoid here. This is all two-dimensional. It's actually a truncated cone. Like that. That transfers load. And then in this material, there's another one here. That transfers load. And a third one here. Any questions about that picture on the board? That is the path through which the load is assumed to be transferred or connected from the underside of the bolt to the top of the nut, going out somewhat. Once you get out here, it diminishes appreciably. That's why when you want to connect two plates together or two parts, and if they're long, you just don't just put one bolt here and say, okay, the whole thing is connected. Well, out here, that connection is not very much. That's why you need 2 bolts, 5 bolts, 10 bolts, however many you need to make the connection. So this connection, the loads are transferred like this. Then if you have another one that has the same type of load transfer that you see here. As we look at this, we see 3 regions. This one, that one, and that one. Each of which three-dimensionally looks like this. So when I say trapezoid, I only mean 2-dimensional. Does everybody understand that? Each of those is what is called a frustum of a cone or a truncated cone. So we have 3 different frusta here. And as we look at this, well, this is not very much different from this bolt. The only difference is, well, actually 2 differences. This is under tension, that's under compression. That's 1. 2, this has a constant cross-sectional area, that one does not. The cross-sectional area here that carries the load looks like this, all over. And it changes. So what we're going to do is to take a look at one of these frustums, come up with an equation that defines the stiffness of that frustum, a general equation. Then apply it to this one, to that one, to that one. Then say we have 3 springs in series. Use an equation similar to this to come up with the stiffness of the member. Is everybody clear on what we were about to do? So we have a member under compression, which can be assumed to act like a spring, as before. That spring constant. Problem is, A is not a constant. Therefore, we have to integrate in order to find this. So here's what we do. And for that, I'll just refer you to the screen. So here's the frustum in 2 dimensions. This angle alpha is, depending on whose book you read, will be different a little bit, but it's close to 30 degrees. Close to 30 degrees. Your book actually uses 30 degrees. So since the area is changing here, we can't use that equation. But if I take a small element here, dx, I can use that equation. So that small element is that. And I will color it a little bit. Oh, don't want to go in there, although the back is okay. It's like a washer. You can think of it as a washer, if you want. Very thin element whose thickness, dx, and it's situated at a distance x from the top. And now I can find the stiffness for this small element, and then by integration to find the deflection, I can find the stiffness for the whole thing. One question that we will have to answer right off the bat is, what is that? This, of course, is the diameter of the bolt. Big D is essentially the diameter of the bolt head or the nut or a washer that may be used, any one of those. And it's very close to 1.5 times the bolt diameter. So this D, for example, for a bolt like that, is that. We're looking at the top of the bolt. That's the bolt head, and that's the diameter we're talking about. It's about 1.5 times the bolt diameter. And eventually we'll use that in one of the equations. So take a look here. We have to find this area. This area looks like this. This is at distance x from the top. This is the area I'm looking for. That area A is equal to pi over 4 times, call this distance d sub x. The diameter of this distribution at distance x from the top. This diameter. That diameter, of course, is that of the bolt. So we need to find this diameter d sub x. Let me find d sub x up here, and then I'll put it in here. So d sub x squared minus d squared. Agreed? Now, what is d sub x? If you take a look at this picture up on the screen, or the one I have here, it doesn't matter, but this one I think is easier to decipher. The diameter here is equal to that plus that little distance plus that little distance. So let me just draw that over here. Well, actually, I'll use this. It is this diameter I'm looking for. It is D, capital D, plus that distance, plus that distance. Correct? Capital D plus this little piece plus that little piece. Each of those little pieces is, if that angle is alpha, this is x times x is this distance, x times the tangent of alpha. Therefore, d sub x is equal to d plus 2x tan alpha. Any questions? Of course, that diameter is a function of x, as it should be. The further down you go, the larger that diameter. D, capital D, stays a constant, this increases. Okay, then we substitute this on top there, and then we say delta, this is now a, just simply, like I said, like a washer, it's a compressive member. We get compressive deformation of this, d delta. I'm now using this equation. Sorry, not that equation. Equation for delta. I'm using this equation. Axially loaded member. Delta equals FL over AE. But this is just a differential thickness, so I'm using d delta is equal to F times the length of the member in the direction of the applied load, which is dx, divided by A and divided by E. We now substitute that over here. So we get F dx divided by pi over 4 times d plus 2x tan alpha squared minus d squared. All times E. And that's the increment of deflection. If I want the total deflection of this frustum from here to here, I'll just integrate that over that length. X varies for this part, X varies from there to there. Or for a general part, X varies from 0 to T. That's that distance. Therefore, we say delta is equal to the integral of d delta. And that goes from x equal to 0 to x equal to t. We integrate this, and we come up with this equation. Delta is equal to P. I've said F in here, we're using P, so let me just change all of these to P's rather than F, so everything will be consistent. So, corrected? Yeah, I corrected. So what we get is this, P divided by pi E d, little d, little d, tan alpha log of 2t tan alpha plus d minus d divided by 2t tan alpha plus d multiplied by d plus d divided by d minus d. That's what we get. And that's a general equation for any alpha, and it's good for any thickness of the frustum. If we use alpha equals 30 degrees, and that's what your book does. Then we look at that equation. We say the stiffness of this frustum, for which we calculated all of this, the one on the right-hand side in purple over there on the screen, the stiffness of that one frustum can be found if I find Km1, I'll call it the stiffness of the first part of the member, member 1, is equal to P over delta. That'll give you the stiffness of that part of the member. So this is delta. You substitute that down in here, and you will have the stiffness. And with alpha equal to 30 degrees, it will turn into this equation. So Km1, we'll just call it, Km1 is good, equals 0.577 pi ED divided by log of 1.15 T plus D minus D times D plus D divided by 1.15 T plus D times D minus D. That's the equation we find for the stiffness of the member. And notice that the thickness of the frustum is T, the large diameter is D, the diameter of the bolt is little d, and E, of course, is the modulus of elasticity. One very, very important point in the use of this equation. This D, the capital D, in this case is equal to this bolt head diameter. But if you are looking at a frustum in the middle of the pack, this one for example, you have to remember that that D is no longer this. It's that distance. Does that make sense? Because everything is based on the small diameter, and you go from that with the distance x. So the small diameter here is equal to this diameter, also called diameter of the washer. And you can take it approximately as 1.5 times the bolt diameter. So there's the diameter of the washer. That's just more or less the same as that. But if I'm going to calculate this for this part, this middle part, it's equal to that. It's not the top. It's not D at the top. It's the smaller of the two diameters in the frustum. The smaller of the two diameters. Now, if you're looking at the top part here, that's the smaller of the two diameters. You're looking at the middle part, that's the smaller of the two diameters. Looking at the lower part, this green, cross-hashed green one, that's the smallest of the two diameters. So smaller of the two diameters is the one you use in that equation. Once we find that, of course, we can combine all of these. So we find the Km1, Km2, Km3, then we use this equation. And then we say K equals the summation of 1 over Km, or Km, the stiffness of the member, is equal to the summation of Kmi, where I goes from 1 to however number of frustums you have. For each you calculate it, and you use that equation. Any questions? A special case occurs Actually, I should say that that number varies from 2, not 1. I'll tell you in just a second why. So let me change that from 2. The simplest of these occurs when, in special cases, the parts are made of the same material. You're connecting 2 steel plates, 2 aluminum plates. So they have the same E, they're the same material. And so if you look at it, let's say you have a piece like this and a piece like that, both made of the same material. Insofar as this connection is concerned, it doesn't really care that this one has this thickness and that one has that thickness. All it sees is just steel in between. It's as though you had just one piece of steel and a bolt through that. So force diagram will look like this. But now you don't have to calculate 3 frustums because they're all the same. All you need to do is calculate it for this frustum and calculate it for that frustum. You don't even need to do that because they're exactly the same. So you calculate it for one and then find the stiffness. If you do that, this is what you get. Get Km equals, this is now the stiffness of the whole member, the whole thing. You don't need to use that equation, the summation of 1 over Ki anymore. 0.577 pi ED divided by 2 times the log of 5.577 L. L is the grip length plus 0.5 D divided by 0.577 L plus 2.5 D, where L is the grip length. So if they're made of the same material, this is what you can use. There is also an experimental procedure to give you this very same Km if the materials of the members are the same. And that's shown. These are various experiments with this Km. What you get on the side is Km over ED on the vertical axis, and on the horizontal axis, the aspect ratio, or D over L, diameter of the bolt divided by the grip length. And they have come up with the relationship between these two, and that relationship looks like this. Km over ED equals A e to the B D over L. A and B are constants, which are found experimentally, and they're given in a table in your book. This equation is the fourth of these. I guess it's the fourth of these. The Mischke 30, that one. And that's the triangular part. Finite element, which is probably the best approximation you can get, is the square one. And notice that it agrees with that pretty closely. So it's not a bad equation. And it agrees with the 30-degree angle for alpha. You see there's another one with Mischke 45, assuming this alpha to be 45 degrees rather than 30 degrees. Different ones. So you can use any of these that you wish. If, however, you have a system where the members are made of the same material, and that's pretty good to use. I would suggest that you program both of these equations, this one, because you have to use it in homework most likely, and that one, into your calculators and use them. Don't go through calculating these in an exam or a quiz or anything like that, because it's just too time consuming. So program them all. Just make sure that your program is correct, number one. And number two, that when you use that program or equation that you've programmed, then you will tell whoever is reading it what goes into that equation. In other words, D equals a half inch, E equals 30 times 10 to the 6, L equals 3 inches, what have you, and then come up with the value. Any questions?
Just making sure that Km is Km equals to the sum over 1 over Km?
Yes. Sum over 1 over Kmi, as I goes from 2 to whatever number. And the reason why, by the way, I changed that from 1 to 2 is this. You have to have a minimum of 2. There's that one and this one. That's the minimum that you can have. But in this case, they're both the same, so it turns out to be that equation. Any other questions? Bolt strength. Of course, we do all of this in order to find out what forces are being carried by bolts, and to make sure that those forces are safe to carry. In other words, the bolt doesn't yield and all of that. Bolt strength is usually measured by what is called proof strength. As the name implies, proof strength is that strength that the bolt has shown to be able to carry. And it exists, proof strength or proof load, exists for bolts and also chains that I know of. And what they do is when you manufacture either one, a large number, you take some samples, and those samples are usually substantial, they're not 1 or 2. You take some samples and you test these samples. Let's say, for example, for a chain, you test 100 of them and you find that the loads that they carry before the chain falls apart and breaks vary something between 100 to 120. Then you say the minimum proof strength for this chain is 100, the smallest of the values that you got, proven to be able to carry. So we actually should put a minimum over here. The same thing is done for bolts. The values for proof strength are shown in tables 8.9 and 8.10. Depending on the SAE grade that you have for the English system, and also for 8.10 for the metric system, you have the bolt size, what sizes come with what grades. They have some markings too. You can tell them by markings, but that's not something that you should memorize or anything like that. They give you the minimum proof strength, minimum tensile strength, and minimum yield strength. All of the properties of bolts are given there. So you go there and you pick this minimum proof strength, and we use it as the strength of the bolt. Your book says this is a stress so that no plastic deformation occurs in the bolt. That's approximately true. It turns out to be about 90% of the 0.2% offset yield strength. You guys remember 0.2% offset yield strength? In a sigma epsilon diagram, that's called the 0.2% offset yield strength, provided that's 0.2% or 0.002. Proof strength is about 90% of that. And there's a graph in your book that shows all of that. Okay? Any questions? All right, let's take a break. Any questions before I continue? We'll take a look at how to use the proof strength in order to find factors of safety and whatnot. So by going through what we have gone through, we have come up with the stiffness of the member now and stiffness of the bolt, both of them. How much of the externally applied load, not the preload, not the tightening load, how much of the externally applied load goes into each one of these depends on the ratio of the stiffness of the bolt and the member. What I mean by externally applied load, do we have one there? No, okay. Is this. There's one member, there's the other member, cross-hatched, the bolt. You've tightened the bolt. Now you apply these loads trying to separate these two from one another, called the externally applied load. A different picture of that is this. Bolted connection, two members, there's a bolted connection with a couple of washers, externally applied load. This externally applied load is not taken entirely by the bolt. We'll take a look at why not. Consider this analogy. Here are two plates. A plate here that is fixed. This is fixed support, if you will. There's another plate, like two washers, if you will. A bolt. This spring here acts as your member. And we tighten this, or just to a point where the spring is about to be compressed, however you like. But the way it's shown is just to the point where the spring is about to be compressed. So here, the force in the spring is 0. And notice that the bolt protrudes through this lower plate. It's got a little hole here. And you hang a weight here equal to 100 pounds from the bolt. When you do that, since the bolt goes right through that plate, it's going to push that spring, and there will be a compressive load in the spring equal to 100 pounds. Everybody okay with that? If you have any questions, please ask. This is a pretty simple analogy, but it makes the understanding of what I'm about to say much, much easier. Then what we do is we insert a stop here, little piece of steel, put it in there. Take off the 100-pound load. What's the force in the spring? Still 100 pounds, right? The deflection of the spring didn't change. Whatever deflection it had before, it has now. Whatever force it had before, it has now. Now, I come in here and I hang from it, let's say, a 50-pound load. What's the force in the spring? Still the same 100 pounds, isn't it? Because its deflection didn't change. So where did this 50 pounds go? And if that's the force in the spring here, if I cut right there and draw a free body diagram, let's say of the upper part of the bolt and the spring, that means the force in the spring in here is 100 pounds, the force in the spring in here is 100 pounds, and the force in the bolt is whatever I'm hanging from it plus whatever was in it before. But not all of whatever I'm hanging from it. Because remember that when we did this bolt, this spring here shows no change. So not all of the force goes into the bolt. If, however, I hang a 110-pound load from here, well, then that stop comes out, and now all of that force is going into the bolt. Remember that the force in the bolt here is 100 pounds, even though I've hung that 50 pound from it. So none of that 50 pound went into the bolt. Where did it go? And of course, it's not magic. What's the force in the stop in this case? 100 pounds, right? What's the force in the stop in that case? 50 pounds. Because you've taken 50 pounds off of that 100 pounds. So the force is, so all of it went into the member. That stop is now acting as the member. All of it went into the member. Of course, in doing this analogy, we're assuming that this stop here is rigid. Doesn't deform at all. Well, that's not quite true for members. They do deform. So this is not to say that none of the externally applied load goes into the bolt if you have a preload, and this is our preload right here. None of the externally applied load goes into the bolt if you have a preload, but that a little bit of it, a small amount of it only, goes into the bolt, depending on the relative stiffness of the member and the bolt. Now, same thing. Let's take a look at a graphical approach to that very same problem. This is a force deflection diagram to the right for the bolt, because its deflection is positive. It is under tension. To the left, negative for the member. So once we tighten the connection by preloading the bolt, and if we take a look at Km and Kb, and by the way, which one is larger, Km or Kb? The stiffness of the bolt or the stiffness of the member? The answer, of course, is on the screen. But why is that the case? As you can see, that stiffness is much larger than that stiffness, right? Much larger. It's not linear. It's related to the tangent of that angle. If you take a look at the area of the member, it's a very large area. Area of the bolt, relatively small compared to that. The equation that we use and in one case you have a much larger area than you do in the other case. So the stiffness of the member is 10 times, 20 times that of the bolt. It depends on the materials, of course. Now, any questions on this? The preload Fi, we call the preload Fi. Fi compresses the member that much, extends the bolt that much, because the stiffness of the bolt is smaller than that of the member. Now we come in and we add an externally applied load P. As we do so, what happens to the compression of the member? We add an externally applied load after preloading. What happens to the compression of that member? Does it increase, decrease, or remain the same? Got to do one of those. If I apply, after I preload this, so member is under compression, if I apply that, what do I do to that distance? Do I increase that distance or decrease it when I'm pulling it? I increase that distance, right? So what happens to the force in the member? It decreases, does it not? It's under compression to begin with due to the preload. We relieve the compression a little bit. Therefore, the force in the member decreases to the tune of its stiffness. The amount that we increase that length for the member and for the bolt are exactly the same. So, take a look here. This is the compression in the members due to the preload. Once I apply the externally applied load, I take that much off. Delta, delta, that much. So I'm over here now. The same amount is added to the bolt because I'm stretching the bolt now by externally applied load. So this is the deformation in the bolt, that's the deformation in the member. So when we come in here, we find that the force in the member dropped from Fi to this Fm, a change Pm, and the force in the bolt changed from Fi to Fb, which is due to that much deflection. The sum of these two is equal to the externally applied load. And as you can see, because the stiffness of the member is much larger than that of the bolt, the same change in the deformation causes much more load to be absorbed by the member than to be added to the bolt. Therefore, not all of the externally applied load goes into the bolt. In fact, a small part of it goes into the bolt, usually between 15 to 30% or so. Again, it depends on the materials. Any questions? So let's put that into some numbers. So we first preload the bolt, and the force in the member after the preload the force in the bolt and the force in the member are exactly the same. One is tension, one is compression. That's when we are over here on the left-hand side on that graph. That's the force in the two, and that's what we get. When we apply an external load, we change the length of the member or the bolt by an amount equal to this delta delta. It's the same for both of them. So applied external load P, if that is the change in the deformation of the member or the bolt, then it follows that delta delta must be equal to P sub B divided by KB. That's this equation. Well, that's written for the member, but it's the same equation, equation for the spring. That equation. We're using that equation. And where in here PB is part of external load in the bolt. The same deformation is added to the deformation of the member. Delta delta is equal to PM over Km. So PM is part of the external load in the member. But the two deformations must be equal. So we have PB over KB is equal to PM over Km. Therefore, PB is equal to KB over Km times PM. And as you can see, the part of the load, externally applied load that goes into the bolt is related to the ratio of the stiffnesses of the bolt and the member. We do know, however, that if we add these two, because that's all we had, we applied an external load P. If we add PM and PB, we ought to get P. So P equals PM plus PB. And we substitute for PM over here. I'll write PM over here too. PM equals Km over KB times PB. Substitute for PM over here and find PB in terms of the applied external load. It turns out to be like this. That's the part of the externally applied load that is taken up by the bolt. The rest of it goes into the member, into relieving the compression of the member. This ratio is called C, the joint constant. And like I said, it varies somewhere between 15%, 0.15, to about 30% or so, 0.30. The smaller this value, the less of the externally applied load the bolt will take. Okay? Now, once we have applied the external load, therefore, we have that much load in the member, and in the bolt, sorry. Therefore, in the member, we have PM is equal to 1 minus C times P. Part of P must go into the member, part of it must go into the bolt. If that's the part that goes into the bolt, that must be the part that goes into the member. Therefore, the total force in the bolt after applying the load P actually write it for bolt and member. After application of P, F bolt is equal to Cp from the externally applied load plus however much preload you had in it already. This is all tensile now. And Fm is equal to 1 minus C times P minus Fi. Any questions? Now we calculate all of this to make sure of two things. One, that the stress in the bolt does not exceed, oh, I just erased the proof load, that the stress in the bolt does not, this is the force, but we have to calculate the stress. Stress in the bolt does not exceed the proof strength of the material with some factor of safety. That's one consideration. The other is that the force in the member must never become equal to 0. There must always be a compression on the member. If you don't have any compression, you don't have a joint. All of the load will be carried by the member. In other words, by the bolt. In other words, if that happens, you're there. All of the load is carried by the bolt. So these are the two things we need to check for. So one by one, let's take a look. First, we have to calculate the stress in the bolt. Sigma B equals FB over AT, the tensile stress area, remember. FB is that, so that's CP over AT plus FI over AT. I write them separate because that's called preload stress. That's called induced stress due to the load P. But you don't have to separate them. We would like this to be less than the proof strength of the bolt with some factor of safety. We call that factor of safety N sub P. I think your book calls it the load factor. So load factor, but remember that this is the same as factor of safety against exceeding proof strength. And just like all factors of safety that we have looked at so far, we say this. We don't divide, by the way, the proof strength by that and say that's our factor of safety. That's not what you do. Because the factor of safety should come from the externally applied load, not from the preload. The preload is there whether you like it or not. Here's what we say. By what factor can I increase the externally applied load before the stress in the bolt equals the proof strength? By what factor can I increase the externally applied load before the stress in the bolt reaches the proof strength of the material? In other words, when that happens, then sigma B must equal to SP, the proof strength, and that's equal to C NP, that's this factor, the proof load, factor of safety. So it is only applied to the external load, not to the preload. And we now solve for NP. SPAT minus FI divided by AT. SPAT minus FI divided by CP. That's the proof load. That was one consideration. And remember, both of these equations are good. Both of these are good. If there's compression in the member. The load in the member must be negative, or else these are no good. All of the load goes into the bolt in that case. The next factor of safety is that of joint separation. Once again, we go to the member, we say, the force in the member is this. By what factor can I increase the externally applied load before Fm goes to 0? That's called joint separation. So we write that like this. Fm equals 0 equals 1 minus C times NJS times P. That's the factor for against joint separation. Minus Fi, and we solve for NJS. Fi 1 minus C times P. These are the two static load factors or factors of safety that we use. Static ones, of course. Any questions? Yes.
What does NJS stand for?
What is it? What is it called? Factor, load factor or factor of safety against joint separation. You're welcome. Insofar as the proof strength is concerned, sorry, not the proof strength. Insofar as the preload is concerned, that might be a question sometimes, saying, what kind of preload should I use? We have said that the higher the value of the preload, the better the joint. The less of the externally applied load that the bolt will take. That's true. But if we take this all the way just before the proof strength, the stress is just a little bit less than the proof strength, then as soon as you add this to it, with whatever factors of safety you have, or as soon as you add that to it, it's going to go over the proof strength. So you can't load it up right to the proof strength. A good measure is for reusable connections, like pressure vessel heads, that you put on, take off, change gaskets, what have you. Use 75% of the proof strength as your preload, or preload stress. So for reusable connections, proof load. So don't write Fi equals 0.75 SP. That's a stress, that's a load. They can't be equal. Proof load, 75% of it, your preload. This is for reusable connections. Then Fi equals 90% of SPAT for permanent connections. This is in the absence of anything else. If it is already given, then that's what you use. Any questions? Okay, let's take a look at an example problem. This is problem 834 from your book. So it says, problem 834. Oh, I don't have that here. Don't have the picture for it. You can take a look at your book, but it is similar. Ah, that's a set screw. It's similar to this, even though this is a set screw. But the problem that they're talking about, there's a nut here. That's not a set screw. It just goes right through those two holes. It's a pressure vessel head connected to a body of a pressure vessel. So I can put something on the board here. Maybe I'll just draw it very quickly. You get a much better view of it, or it looks much better if you take a look at the picture in the book. But it looks like this. That's the head, and that's the body. And there's a gasket, or a confined gasket here. So this is what the problem says. The figure illustrates the non-permanent connection of a steel cylinder head to a grade 30 cast iron pressure vessel using end bolts, and then they give you the end. Confined gasket seals has an effective diameter of D. I'll explain that in just a minute. The cylinder stores gas at a maximum pressure PG. For the specifications given in the table for the specific problem assigned, select a suitable bolt length from the preferred sizes in table A17, then determine yield factor of safety NP, load factor of safety NL, and joint separation factor NO. They said they calculate both the yield factor of safety and proof factor of safety. If you have a factor of safety for proof larger than 1, it's certainly larger than that for yield, because the proof load is about 90% of the yield load. But if you want to calculate it, that's fine. So this business about the sealing diameter. If there's pressure inside of the cylinder, then that pressure doesn't stop here, because you have two pieces of metal here. It's not going to stop any pressure. Pressure is going to get in there. There's still going to be pressure here until you get somewhere to the middle of this, not exactly the middle, somewhere to the middle of this. Sealing diameter is the diameter for which the pressure is confined. It will not escape past that. That's called the sealing diameter. And it is not equal to the internal diameter of the cylinder. It is larger than the internal diameter of the cylinder. It may even be larger than the external diameter of the cylinder, depending on where your gasket is. So don't even deal with either of those two diameters. Just sealing diameter given, use it. Why do you need it? Because you have to calculate the externally applied load, which comes from the pressure vessel and tries to push that head up. And you have to know what area it acts on so that you can find that force. So you use that to find the force. Now let's first you need to find the bolt length. To find the bolt length, you have to go to the particular problem, of course. 834 says these various dimensions that are given in this problem. What is important is the sealing diameter that I've already given you, and these two thicknesses, this one, which is 1/2 inch, and that one is 5/8 of an inch. Remember, this is cast iron, the head is steel. So the bolt length that we need is equal to that length plus that length plus the nut height. And whether or not you want to add a couple of threads in here, it really doesn't matter. I wouldn't in the beginning. Calculate what length you need, because most likely you're going to have to take something larger than that. You're not going to find that in the tables. You're going to have to take something larger than that. So let's see what we get. So here it is. Grip length. That's from here to here. The sum of these two thicknesses. There are no washers in this case. 1.125 inches. So, and nut height is 7/16 of an inch from table 831. Therefore, the bolt length must be larger than 1.125 plus 7/16. That brings the bolt right up to here, right up to there. But of course, you don't find that in the table, so you use 1.75. So you've already got your two threads that are supposed to be protruding, so no reason to add that. The threaded part of the bolt is 2D plus 0.25. Remember, that's this. I went through these last time. That's LT. That's LD. And if the nut is here, that's little lt. We need little lt for the calculation of bolt stiffness. So LT, this big one here, is equal to 2D plus 0.25, comes from the tables that I gave you last time, 1.25 inches. LD is the difference between the length of the bolt, the total length, and LT, 0.5. And this equal sign here, please change it to an arrow sign. Obviously, LT and LD are not equal to one another. So please change this to an arrow going to the right. And little lt is equal to the grip length minus LD. Grip length minus LD, 0.625 inches. AD is the area of the nominal area of the bolt, pi d squared over 4. AT you find from the tables in the book. The equation for bolt stiffness, you have AT, you have AD, Unless otherwise specified, the bolt is steel. So you use 30 times 10 to the 6 or 29 times 30 to the 6. Here I've used 30. That's that's the stiffness of the bolt. The member now consists of 3 different frusta. This is the total grip length. That's capital D for the top frusta, capital D for the bottom frusta. These are our 2 load distribution lines at 30 degrees. And notice that the top part is steel, so you have to calculate a K for that. This middle part is cast iron. You have to calculate a K for that because it's like that. And then the bottom one is also cast iron, a different K for that. So you have 3 parts to the stiffness of the member, Km1, Km2, and Km3, and you have to combine them. So you have to use this general equation, and this is for the steel, for that top part. And this is general equation with these values. T equals ½ inch. D, diameter of the bolt, ½ inch. Capital D, 1.5 times the diameter of the bolt, 3/4 of an inch. Nothing else is said, just take it at that. Usually the washer diameter. And E is 30 MPSI. Put them into this equation, you come up with 33.3. For the middle part of the member, this one, be very, very careful now to make sure that you put in as capital D this distance. That's what's done over here. So cast iron will have 2 frustra as shown. Midpoint of the grip is here. That's the midpoint of the grip. So this thickness can be found by subtracting 0.5625 from 5/8 of an inch. This is the upper frusta, 0.625. Now, for the middle one, we have D still equal to 0.5, but capital D is that distance, which is 0.75, that, capital D, plus 2 times 0.5 tan 30. Those 2 little pieces that I was talking about when we did this, that come from the distribution of the load. You put them all in that top equation again, and you find another value for an E of cast iron, of course. You find another value for the stiffness of the cast iron member in the middle. And finally, it's the bottom part, this one, third part. For that, D and T are the 1.5 times bolt diameter and half the length of the grip. So there's T, half the length of the grip, 0.5 diameter of the bolt, diameter of 1.5 times diameter of the bolt, or capital D. E for cast iron, you calculate that, and you get its value 15.26. Now you combine all of these. So Km equals 1 over Ks plus 1 over KCI1, KCI2, all to the -1. It's the same equation. 1 over K is equal to the summation of 1 over Ki. Exactly the same. So that's what you get. C, the joint constant, is Kb divided by Km plus Kb. In this case, comes out to be about 30%. And here I say load factors and factors of safety will be calculated in another example. So we'll go to that example to show you how that's done. Although that example includes a little bit of fatigue as well, which we have not done. So we'll just go over the first part of that example. Here is that example. Now, to calculate factors of safety, load factor, we say assume, this is the same problem continued. Assume the pressure inside the cylinder changes from 0 to P. For our purposes, just think it's P. We're doing statics, we're not doing fatigue yet. So P, which results in an external load of 2 kips per bolt. The pressure inside the tank is P, and forces up the head, producing for each bolt a force P, external force, equal to 2 kips. If the bolts are SAE grade 5 and are preloaded to 75% of their proof strength, check out relevant factors of safety and load factors. And remember, we're only doing statics now. From table 8-9, we get proof strength equal to 85 KSI, tensile strength 120, yield strength 92. Never mind SE, I'll talk about that when we do fatigue. That's the endurance limit. Preload is 75% of the proof load, 0.75 SPAT, 9 kips. Force in the bolt, CP plus FI, these equations that we had here. Force in the bolt, CP plus FI, C, there's the externally applied load, 2 plus FI. Proof factor of safety is this equation. And you have everything in that equation. Proof strength, AT, FI, C, and P. You get 4. Joint separation, this equation, Fi divided by 1 minus C times P. And there's your Fi, 1 minus C times 2, equal to 6.4. So those are factors of safety for static loading. And at this time, that's all we're able to calculate. There is a factor of safety due to fatigue, but we will do that next time. So on Tuesday, if there is a quiz, it will cover bolts, threaded fasteners, power screws, up to, but not including fatigue. So I have not done fatigue, so that will not be covered. Okay? Have a good weekend, and I'll see you on Tuesday.